these glasses off to the left and right.
It means it probably went a little further down than it went up, so you pushed a little, maybe you hit the ground a little harder.
So do you want to go towards the picture?
You see that wiggle around here. And, well, when the kids come by, the first question I ask is whether they think that those little thingies that you see wiggle around, whether they're dead or alive. It's amazing.
There was an interesting study done on people who work on insects. Scientists, and they have to use insects. They develop or just study them.
So basically what he did is to measure the trajectory of these particles. And
they were
if you do that carefully, then
1% of the
you can deduce with Einstein's theory, using Einstein's theory and your measurements, you can deduce how large molecules are. And that's pretty neat, right? Because you can just do it by looking. Just rotate this thing. You see it happening?
No. Yeah.
So,
Well, I was going to say.
it's completely washing out. And now I'm going to rotate it back. And there. Get it again.
If you can get a good picture of a track in there, you'll be lucky.
Working well.
If you have a camera, that a motion, I mean, if you're running video, then that's good.
The US is that's a camera. Camera is very penetrating.
So that's 1,000.
That's a camera.
But a still snapshot is difficult to get.
That's not
Yes, it was smaller and get about 30% CMS.
It's radioactive. So this is radioactive material.
Missing energy. And from that, it's electrons right here.
That's really interesting.
Well, it's going a little bit faster, right? Well, it's going in and
Yeah, see?
balance. Very distracting.
So if you notice, it's a small noise, that's normal thing. But if you
So the light cloud doesn't have very much energy. It's not totally right, right? So onto it. And the light cloud moves really fast. It's heavy puck. Let's go to the next room, okay?
okay. You want to try it? Go to the left and I can catch it. Yeah. Fast.
Can you feel it?
causing rotation. And if I turn it off, it keeps going because it's got inertia. It was moving, so it continues moving until friction stops it.
Okay, yeah, that's essentially it. I mean, you get these things called nodes, right, which are basically points that you get points that don't move at all and points that move quite a bit. And so the sand is kind of aligning itself in the points that don't move at all. So if you stop by this station first, you can see it with the spring a little bit more in one dimension. It's a little easier to visualize. Because when vibrating in 2 dimensions, you get sort of this geometrical.
Rod, you do this with like some rosin down it, and it's just screams.
Now we're jumping to a different frequency, and so the regions where there's no motion change at different frequencies.
And just straight down real fast.
Wow. There you go.
Oh, what a bad shot.
Really like toss soccer balls.
Am I going to throw up?
No, you toss the soccer balls. That's all you have to do.
Are you even taking my dog? I'm like, no. Why would I do that? And he goes, Billy, why you fucking up? I'm like, in my pocket. He goes, Brayden!
It's all random.
Yeah.
I had to look up what it is.
Yeah.
The professor was explaining to me. I didn't understand. So yeah, if you're increasing heat, it's gonna be like more energy exchanging between 2 electrons.
We turn the light on. We bring it closer to the motor. And as we bring it closer, the motor's moving faster. Pretty fun stuff. And then this produces about 100 watts of energy. The problem is, a single person requires about 1,000 watts. So for one person, it takes 10 minutes.
I like the evil that side.
It's doing the icing model, so it's like a cellular automaton. Each cycle, it looks at its nearest neighbors. Yeah, I don't know exactly how it works. You have to look it up. But it's basically magnetic domains.
So the lower.
You're good at it. Come on. You can do it.
There you go.
I mean, they're beautiful and everything else. With volcanoes.
But if I put it in liquid nitrogen, it will change its properties dramatically. So we're just going to put that in a little cup of liquid nitrogen, and it's cooling off. And as it gets cooler and cooler, you'll see that its properties change. And you can see, actually, the liquid nitrogen doesn't bounce like it did before. And I want to get it a little cooler, and then I'm going to go somewhere where I'm not going to hurt anybody, and I'm going to show you what happens. So let's see. It takes a little while to cool it off. Hopefully it's cool enough. And it smashes quite easily. Not elastic at all yet, but it's going to warm up, and so will the other pieces on the floor, and it will return to its former state. So another fun thing we can do with that concept is we have some little rubber tubing, and we have some nice bananas here, and we have, that's not working out very well, is it? So let's cool those off, and let's cool off this banana. And we'll see that their properties change a bit. And we'll see what happens with that. Yeah, that sounds a little different now, doesn't it? It's the banana takes a little longer to cool. And the banana will get nice and hard. I hope it is, because it makes a real mess if it isn't hard. So I have my nail now. It's not as hard as I like, making a hole in the banana, but it's, well, we'll put it back in. It's partially successful at so we'll try it again. No, don't touch it. It's going to look a bit different. So initially, it's frozen and looks the same, but in a few moments when it warms up, it's just going to collapse. Okay. Pull balloons out of the viewer. And that's not all. That's better than putting those rabbit and you can see that all that fit in our little viewer. And hopefully they'll be just fine, unlike the rabbits, and they don't have to be fed. It's nice. They don't have to deal with, right. So that's as close as we get to being magicians, except so that's because of what's called the Meissner effect. The superconductor doesn't like to have the magnetic flux from the little permanent magnet go through it, and that levitates the little magnet. Okay, so I think that's all the demos we have for you this morning, and if you'd like to come
there you go. Yes.
You can fly.
You can get a video. Hurry up and get a video. Here. Before it drops again. Got like the perfect angle. Got the perfect angle.
Need some more liquid nitrogen.
Using the volume control you can zoom, so. I like how now the magnet thing is white and it used to be like shiny and silver. All metallic looking.
Which one, the one on top? Look at it with your own eyeballs.
Water's condensing on it, so it's because it's so cold.
Yeah, it has some condensation.
Freezing.
Yeah, you can see the liquid nitrogen boiling around it.
No.
Oopsie.
Come back.
What's going on there? The science forum? That's it.
Oh, maybe after this one. I'll go back over there.
Okay.
And then come back here.
So all modern day telescopes, we don't get the pleasure of using it for ships to move them around. They're all moved with computers.
That freezes.
It's like through water.
Tell already. Stick it in there. Is it cold? I wonder. Jeez.
Oh, jeez. Oh, jeez. Oh, that is cool. That was cool. Oh.
Oh wow. News just in. The city of Swain is in complete uproar after all of its superheroes have been found to be missing. They've completely disappeared, and now everyone is wondering what the city's going to do. In fact, this article says that entropy has increased 300%. The article says that Dr. Doctor has set up a series of trials and tribulations for various people to come and try and solve that require physics expertise, and only if they can explain the phenomena behind his challenges and complete them will he release the superheroes.
Doesn't Dr. realize physicists read the newspaper?
Apparently not.
Oh well, let's get over to Swain and see what's going on.
Superheroes in the city of Swain. It is in complete disorder. It is in disarray. And no one will stop me from completing my due
Let's go.
and my thesis. Release us!
Let's go.
Let us go.
Diagrams, and won the 1965 Nobel Prize for my work in quantum electrodynamics with 2 other physicists. I'm also famous for popularizing physics with my colloquial nature and talkative style that made it so people can understand physics and kind of grapple with it on a more individual level.
You look very good for being 95 and dead.
And what can I say?
I'm Rosalind Franklin. I'm a biophysicist who helped in the discoveries of DNA, RNA, viruses, coal, and graphite, as well as my X-ray images led to the understanding that DNA has a double helix.
All right. I think I've heard of you. You two seem as though you might know some physics.
Now, you can see that we have potato on both ends. Easy? Yes? Okay. Now, using this rod, I'm going to launch this piece of potato. Those of you over there might want to watch it out. A finite number of air molecules and a finite volume. But then, by pressing on one of the chunks of potato, I was able to decrease the volume, which caused an increase in pressure, pushing the other piece of potato out in a stupendous explosion.
Each color, what each salt is. Red indicates lithium chloride. And this one, orange, is calcium chloride. This purple color means potassium chloride. And this green is copper oxide. Meaning that this yellow is your nice sodium chloride or normal table salt.
Very good. Very good.
Born in 1858, and I'm most famous for my work in quantum theory. I got a Nobel Prize for it in 1918, kind of a big deal. And I basically established the modern theory of quantum physics.
You look very good for...
Looks like you have this under control. We'll let you handle it, Knox.
Thanks, guys.
Very well.
All right. There's another coil. It's much bigger wire, and there are much like 10 turns on this one. What happens is it takes the voltage from the wall, sends it through that coil, which creates a magnetic field. Now that induces a current or voltage gap between the smaller coil and the larger coil, which you can kind of see up here. With the large coil, we've got a lot of electrons, and the small coil, we don't have very many at all. So that gap keeps getting bigger and bigger and bigger and bigger. It's Louis de Broglie, Mr. Doctor.
It's Dr. Well, I guess it's Mr. Doctor. So it's not really Doctor.
Yes, I am Louis de Broglie. I'm a French quantum physicist, and I'm most famous for my research on wave-particle duality. I discovered that electrons exhibit both wave and particle properties. And for that matter, all other matter has wave and particle properties too. Yeah. Well, this are real nails. They are real nails, but I'm not scared. Because there's so many of them, you made one mistake, there's so many of them, that when I lie down, the weight will be evenly distributed. And I won't be hurt at all because of the pressure on each per nail being so low. Nasty.
Save that for later.
Comfortable.
Where's Bob? Where's me?
Exactly.
Yeah, make sure he gets the face shield. We want him to look good. Superhero, above average metabolism, man. Can you lift your sledgehammer? Or you? All right.
So, everybody cross your fingers.
You died.
Yes. The reason I didn't die was because when the sledgehammer was swung, all the force went to the breaking of the cinder block instead of being transferred to actually hitting me on the nails. So instead of it, pushing me down, all that shattering and this stuff going all over the place and making a big mess for janitors, we want the force to transfer.
I'm Jocelyn Bell Burnell. I've been a professor at several universities, and I've been president of both the Astronomical Society and the Institute of Physics. I should be well known for my work on pulsars, but I got cheated out of the Nobel Prize on that one.
Remember, now you got this.
Well, perhaps your brains may not come in as much handy as you would think for this challenge, because I would ask you break a racquetball. And this seems maybe at first an easy task, not allowed to use fire. And these are really squishy, very hard to Good luck smashing it.
That's really not that hard. In here, I have some liquid nitrogen. It is very, very cold. So, when things get very cold, the molecules in them tend to slow down. And it becomes easy to break them because they become very rigid. For instance, if we have this normal banana, you can look at it and see that it's very flexible, it's not hard to crack. However, if I take this banana that has been sitting in liquid nitrogen for a little while,
So you brought your cold bananas.
I did bring the cold banana. And I dropped the cold banana. But as you can see, it is very easy to crack and break. Now, another cool thing you can do with this liquid nitrogen is you can take this balloon and stuff it down in here, and it'll shrink because the air molecules are slowing down. And then if you take it out, it gets big again as the air expands because it's heating up. Now, you want to see this ball break? Well, as I've shown, it really shouldn't be that hard. This ball was rubber a little bit ago, and it still is rubber now, but it's a lot cooler. And so, it should be easy to break.
What are you?
I'm really good with Microsoft Word.
And what is your power?
Super thighs.
Microsoft Word girl, let's go. You're definitely. However, you will have a lot more work to do before you can save your friend Kevin Supercross.
Well, I think I'm up to the task.
Oh, wait, now you're Erwin Schrödinger. I've heard of you. I've heard of your dad. Okay.
Yes, that's right. I'm Erwin Schrödinger. I'm a famous 20th century physicist. I made great contributions in the field of quantum mechanics with my wave function. And I'm also fairly well known for my thought experiments, which is kind of coined now as Schrödinger's cat.
Very well. So what regular decay by now? I think my experiment is giving some kind of like time.
Yeah, well, at least I got a Nobel Prize in 2. So. We got some more challenges?
Yeah, minions. Minions.
Easy.
Okay.
You see, sound travels in waves. Just like when you drop a rock into water and you see it ripple out, sound also travels in waves of alternating high and low pressure. So here we have a tube which is full of...
pressure on this tube.
Yeah, it looks like there's no pressure, but... We have a tube and it's full of propane gas like you use on a grill. And when we push sound waves through it, the pressure of the gas alternates between high and low points. And then the flames you see, as a result, have either more or less gas, and you can see waves. So if we apply a sound, such as a tone, you can see, with a larger volume, you can see both high and low points. And as you change the frequency or the tone that you're applying in the tube, the length of the wave changes as well. And so when you apply music, you can see a bunch of different waves at once. And the flames can jump around.
I'm Albert Einstein on a bad hair day. And, so you probably know me best from coming up with the theories of special and general relativity. A really famous prediction of special relativity is that particles can't travel faster than the speed of light. Sometimes if you have a cable loose, you think they do. But general relativity is our best explanation of gravity. Is that you do not flinch. Ah, you didn't flinch. Still, how are you going to crush it without super strength? Well, can't you use your Yeah, what powers do you guys actually have? You're so weird. Oh, that's super fast. Well, yeah, you actually don't need super strength to crush this. Let me explain. So all you actually need is physics. So when I close this valve, there's a spring. I'm going to cool this down, and hopefully I can crush this. Albert Einstein was not an experimentalist, so we'll see how this works. So I'll explain it a little bit. So what happened was there was a little bit of water in the bottom of this oil drum. And we've been heating it up for a little while, hopefully for long enough, so that the water boils into steam, and that evacuates the air in the oil drum. And once the air is evacuated, and we turn the flame off, the steam condenses back into water. And what should happen, and should be happening really soon, is that the air pressure is strong enough, atmospheric pressure is strong enough to actually make this implode, because this has a pretty big surface area.
You maybe need some help from your superhero friends.
Yeah, somebody gets sledgehammer.
You maybe need Mighty Thor.
That's great.
Come on, Thor. You got this, Thor.
I don't think we need one more.
Now we try. So sometimes physics is a little bit unpredictable. But can we get everyone out of here?
It looks like physicists are the real superheroes.
Questions afterward. We're going to do a few of the demos. If you want to come down here, check it out, talk to the scientists. Okay, we have questions.
Everyone, slip through you. Oh, it's Christmas time. Yeah, come on down.
Okay, thanks.
So that was all the pressure that was in there.
Do it for a long period of time.
That's